Black holes, considered among the most baffling and extraordinary phenomena in the universe, persist in sparking rigorous investigation and enthralling the attention of both observational astronomers and theoretical physicists. These cosmic objects, defined by their tremendous gravitational power and total absence of emitted light or radiation, epitomize a boundary beyond which conventional physics fails. Originally proposed by Albert Einstein in 1916 as a consequence of his theory of general relativity, black holes remained largely hypothetical until advances in the 20th century made indirect detection possible. A major breakthrough transpired in the 1960s when researchers studying the Cygnus star cluster encountered an anomalous cosmic irregularity, a luminous blue star emitting potent X-rays. This star, orbiting an invisible companion, contradicted traditional interpretations until it was validated as being gravitationally bound to a massive black hole, eventually named Cygnus X1. The discovery of Cygnus X1 furnished conclusive proof of the reality of black holes and heralded the beginning of a transformative epoch in astrophysics. Located about 6,000 light-years from Earth, Cygnus X1 exhibits astonishing properties. It possesses an extreme mass density and produces such a formidable gravitational pull that even photons cannot escape its grip. This distinctive quality inspired the name black hole, a succinct expression conveying the enigmatic nature of these space-time anomalies. Subsequent exploration revealed a diverse array of black holes dispersed throughout the cosmos, with estimations suggesting that the Milky Way galaxy alone could host over 100 million. Despite their elusive character, which makes direct detection exceedingly difficult, astronomers have identified several likely examples within our own galaxy. From stellar mass black holes, arising from the death of massive stars, to supermassive varieties situated at the centers of galaxies, their influence extends well beyond their immediate surroundings, significantly shaping galactic evolution and altering the trajectories of nearby stars and other bodies. Anything that ventures too close is irresistibly drawn toward the event horizon, the critical threshold beyond which return is impossible, where it undergoes extreme gravitational stretching before being absorbed by the singularity at the black hole's core. This remarkable effect, called spaghettification, exemplifies the overpowering force of a black hole's gravitational field. As an object approaches the event horizon, the gradient in gravity between its nearer and more distant sides becomes so severe that it stretches and deforms the object into a slender, elongated filament. The black hole's pull surpasses the object's structural integrity, ripping it apart and pulling it inward toward the singularity. Although black holes offer a singular environment for probing the limits of physical laws, they remain deeply mysterious. The quest to decode their secrets continues, propelled by humanity's profound desire to grasp the fundamental architecture of space-time and gravity on the grandest scales. These enigmatic objects act as silent guardians, driving scientific advancement beyond the boundaries of current comprehension and testing our intellectual limits. Even though the nearest confirmed black hole lies approximately 1,500 light-years away, worries about their potential impacts endure. In 2021, scientists achieved a historic landmark by capturing the first authenticated image of a black hole, specifically the one residing at the heart of the M87 galaxy. This accomplishment yielded crucial insight into the internal behavior and dynamics of black holes. The image revealed that black holes possess layered complexity, challenging the oversimplified view that they are mere voids. Through meticulous analysis and reconstruction of observational data, researchers discerned three fundamental regions within a black hole. The outermost zone is the event horizon, the vital boundary beyond which nothing can escape. Beyond that boundary, gravity dominates absolutely, drawing in all matter without any possibility of egress. Deeper inward lies the photon sphere, the second layer, where light loops perpetually around the black hole. Any photon entering this region becomes ensnared by gravitational forces and cannot escape. At the innermost level resides the singularity, the core region where classical physics utterly fails. All established scientific laws collapse there, sending physicists into realms of speculation and theoretical ambiguity. The intricate and distinctive behavior of black holes presents formidable barriers to full comprehension. While many conform to the canonical three-layer structure, each black hole exhibits individual traits that complicate classification. Accordingly, conventional research techniques often fall short, necessitating more inventive strategies. Because physically entering a black hole is impossible, any probe would be destroyed by the extreme conditions. Scientists rely on indirect observations as their chief means of investigation. Nonetheless, investigators remain resolute in their effort to uncover the truths behind these immense cosmic forces. Multiple conjectures, ranging from stellar collapse to gargantuan cosmic events, offer plausible accounts of how black holes originate and operate. One prominent example is NASA's study of the M87 nucleus, which provided strong evidence of a supermassive black hole exerting dominion over vast stretches of space. Still, the drive for total understanding continues, powered by human curiosity and relentless ambition. Even though black holes might resist complete elucidation, sustained scientific exploration could ultimately uncover the most secretive corners of the universe and decode its most profound mysteries. In 1963, physicist Roy Kerr proposed a revolutionary theory concerning rotating black holes, fundamentally shifting earlier scientific assumptions. A central element of Kerr's theory is the ergosphere, a surrounding region of the black hole in which opposing energies momentarily halt further collapse. This unusual zone manifested unexpected qualities that defied mainstream physics, hinting at even deeper strata within black holes. Among the most intriguing ramifications of Kerr's model was the notion of the Einstein-Rosen bridge, also known as a wormhole, a speculative passage through space-time connecting remote parts of the universe or perhaps even distinct universes. This idea stems from the interwoven structure of space-time, as depicted in Einstein's theory of relativity, in which large masses warp space-time and influence the trajectories of adjacent objects. Wormholes are envisioned as potential thoroughfares through the cosmic fabric, possibly enabling swifter travel across enormous distances. Yet skepticism remains regarding their stability and real-world applicability. While they spark imagination with the possibility of exceeding light speed and bending time, serious obstacles, such as quantum instability and intense radiation, undermine their feasibility. Moreover, Einstein's field equations impose strict limits on how fast anything can move through space-time. Even if wormholes could be stabilized, they might still not permit speeds surpassing light, regardless of how science fiction portrays them. Despite these enduring doubts, wormholes persist as powerful symbols of scientific imagination and aspiration, named after the theorists who first conceived them. They propose exhilarating concepts and alternate worlds, prompting deep inquiry into the nature of existence and what might lie beyond human perception. The ambition to devise a universal explanation that fuses gravity with quantum mechanics has long driven efforts to formulate a theory of everything, a unified system that brings together all fundamental forces and particles. This quest is kept alive through conjecture, dialogue, and daring intellectual advances. Leading the effort is the prominent physicist Moku, whose pioneering work has propelled superstring theory, a significant refinement over traditional frameworks. According to this theory, the smallest building blocks of matter are not discrete particles, but ultra-minute oscillating strings, akin to those of a musical instrument. These linear filaments vibrate at distinct frequencies, generating the vast array of particles and forces we observe in the cosmos. Within this framework, the universe is comparable to a grand symphony, with each particle corresponding to a unique vibrational signature of these fundamental strings. A particularly captivating aspect of superstring theory is its capacity to explain rare cosmic phenomena, such as black holes, wormholes, and other extraordinary effects predicted by Einstein's models. As these strings traverse space-time, they have the ability to twist and reshape its very structure. Yet beneath the elegant beauty of superstring theory lies substantial complexity, chiefly its dependence on more than the usual 4 dimensions. These extra dimensions remain concealed from view, Although analogies like fish gliding over the surface of a pond, oblivious to its depth, help to illustrate the notion of higher dimensional reality. These hidden dimensions, tightly curled like ancient scrolls, are too minute to detect, yet they influence the fundamental architecture of the universe. Although still enshrouded in uncertainty, they could account for the universe's evolution and the distribution of matter within it. Moreover, superstring theory has revitalized mathematical physics, unveiling profound relationships between abstract mathematics and observable physical phenomena. The drive to build a unified theory has spurred interdisciplinary collaboration, highlighting the deep connections between theoretical mathematics and empirical science. Nevertheless, despite its theoretical elegance, superstring theory lacks firm empirical support. Its reliance on hidden dimensions poses major challenges, keeping it largely in the domain of conceptual inquiry. Still, its revolutionary ideas continue to inspire scientists and visionaries, propelling humanity along a path of extraordinary discovery. As we advance deeper into abstract scientific frontiers, guided by the promising perspective of string theory, we gradually approach resolutions to the ultimate riddles of the universe. Positioned at the threshold of a new era in science, the goal of understanding quantum black holes remains a foremost objective for those resolved to reveal the foundational principles of existence. Despite numerous endeavors, a definitive answer continues to elude us. This prompted Edward Witten of Princeton's Institute for Advanced Study to remark that superstring theory is 21st century physics that arrived by mistake in the 20th century. However, recent advances have reignited enthusiasm. Multiple scientific groups have lately achieved significant breakthroughs, suggesting that string theory might eventually account for everything via a simplified two-dimensional framework, rather than the conventional 10-dimensional construct. Although this progress is encouraging, the journey toward full comprehension remains intricate and demanding. The aspiration to formulate a unified scientific model impels us to venture into the most remote expanses of known reality, where the border between what we can observe and what we can only theorize begins to blur, and where the deepest truths of the universe await revelation.